Todd that you've heard from earlier. I'm on the Minnesota Stormwater Research Council. It's a fabulous part of my job, and I love working with John and Jesse and the other council members. It's a great opportunity. And welcome back to this afternoon. I think we've got a lot of fun things in store still. And thank you for everyone for staying the whole day. We appreciate that. We are going to be hearing a couple presentations from about 1 to 1:55 on pond treatments. And first we'll be hearing from Dr. John Gulliver, who's Professor Emeritus and is working with the University of Minnesota St. Anthony Falls Laboratory. So let's welcome John.
Well, it's very much a pleasure to be here. This is a great conference. I'm surprised it turned out so well, John. I was never I was never too excited about the idea, and I just think it's really fantastic because we're exchanging a lot of very valuable information. I learned something yesterday and today, so that's a good thing, I think. Is my presentation up? Okay, good. So I'm going to talk about stormwater pond treatment. So we have been investigating, talking about what ponds are made of, how they are investigated, the types of information that you need to figure out if your pond is working or not. I'm going to talk about what you can do to take care of a problem pond. So we have a wide project team here. Myself, Purnima Natarajan, Dr. Purnima, Dr. Ben Janke, Dr. Bill Herb, Jacques Finley, and Joe Bissoff. We're all working on this project. Myself, Jacques, and Joe. I'm actually going to talk about 3 projects, okay? But myself, Jacques, and Joe are the PIs, but the people who really did the work are Drs. Natarajan, Janke, and Herb. And you'll see that throughout the presentation. So, I'm first going to start on a little bit of background on ponds. I don't think I need much background. Then I'll talk about a pond phosphorus model that has been developed. We're calling that min pond. And we work into field comparisons because you have to get in the field. A model is never enough because it is always wrong, right? And of remediation techniques, and then some conclusions. So I think I skipped all the background, so which is good because we had it all week long, right? So for both days. So I'll talk about the pond phosphorus model, min pond. It was developed by Bill Herb. He added sheltering and floating plants to Min Lake. And we had a few other things that we emphasized in that pond. And there are quite a few things that are surprising, I think, about duckweed. One is that duckweed in the fall does not disappear. You wonder where it comes from. Where does duckweed come from? It's not there in the spring, and suddenly it's there in the summer. Duckweed doesn't go anywhere. It just falls to the bottom of the pond. So it's living there in the bottom of the pond. And that's why when summer comes and the temperatures get right, when they get high enough, duckweed comes right back. So it's a data-intensive model. That means it requires a lot of data. It requires a lot of field data. It gives you profiles of temperature, dissolved oxygen, and phosphorus. It was developed from a model by Heinz Stefan and his students. It was developed over many years, and it was just converted into Min Pond. So we converted Min Lake into Min Pond. Now, you might be saying, well, what are you guys doing? You doing all this in a computer model? I don't trust computer models. Well, here's my answer to that. This is a fairly well-known quote by George Box. All models are wrong, but some are useful. And I feel this one is a useful model. We can kind of do some things that we can't do in the field. We can do them before we get in the field. And we can eliminate a lot of things that will really not work in the field. as long as we know what our assumptions are and are they correct or are we not sure if they're correct. So we're going to talk about, these are the 5 things that we tried in the model: chemical treatment of sediments, smart ponds, or adaptive control technology. That would be where you have some technology that allows the pond to decrease in depth when there's a storm coming in. Does that make any difference with regard to phosphorus release from the ponds? Mechanical aeration and mixing, reduced sheltering, and watershed treatment. We can do that in this pond model. Like I said, the pond model is highly data, requires a great deal of data. So we took a lot of field measurements. These are the ponds that we worked on. We studied 6 ponds. The maximum depth varies from 1.2 meters to 4.3, so there's a wide variation of maximum depth, a wide variation in pond area, 0.84 up to 4.1 acres in pond area. 3 of them had floating plants and 3 did not, which is a nice combination. And there was submerged vegetation in some of them. And this is the types of data that we have to take to supply to this model. We need 5 profiles in each pond of temperature, DO, and conductivity. We're measuring conductivity so that we know what the chloride concentration is. 5 samples in surface of total phosphorus and orthophosphorus concentrations. 1 sample in the bottom of total dissolved and ortho concentrations, and continuous recording of wind and profiles and depth profiles. And then 5 cores of sediments. So we evaluated the cores in the lab. We determined the phosphate release, and that's something that Dr. Natarajan talked about, and we worked on the sediment chemistry. So this is the types of field investigations at each of these ponds. 5 points, 5 locations in each pond, depth profiles, surface and depth concentrations of phosphate, dissolved phosphorus, and total phosphorus. We also took some continuous measurements of dissolved oxygen, temperature, and wind. And there's an interesting aspect of dissolved oxygen measurements here. One is that I'd like to point out. One is that if you take a look on the upper left corner, that's the Camden pond in Minneapolis, and then that's in 2023, and then if you move one over to the right, you get the Camden pond in 2024. The dissolved oxygen is very different from those 2 years. This is the kind of change you see based upon the weather. So in 2023, there were lots of mixing events. The mixing events are the periods where you have high dissolved oxygen. Where you have low dissolved oxygen, basically 0, is where you don't have a mixing event. So 2023 was not a bad year for that pond. 2024 was a bad year for that pond. A bad year in terms of phosphorus release, because there was so much internal loading from the sediments to the surface of the pond. The sediment characteristics are also interesting. I don't want to go through all these data, but there are a few things that are of interest. One would be Shoreview Commons, where we treated the sediments with iron filings in 2021, and then went back in 2023 and did an anoxic survey. The anoxic phosphorus went to 0. Anoxic phosphorus release, that's phosphorus release with 0 dissolved oxygen in the bottom. And it went to close to 0 right after we applied the iron filings, but then it came back a few years later. So it's at 1.9, which is still below the 5.8 that it had before we applied iron filings, but it didn't last for that long. It starts to come back. The other thing is that that pond had a huge oxic release of phosphorus. That would be the degradation of organic material that degrades quickly and releases phosphate into the water column. So that had about 4 milligrams per meter squared per day release before, and afterwards it still had minus 0.01. So there was an increase or an improvement in this pond, just not as much as we had hoped. And we still aren't sure why the iron filings work. I came up with a justification that I think might be pretty good, and that is that we basically overload the system with iron. So you have so much iron in the water that you have precipitation of ferrous iron, that would be Fe+2, which is normally soluble. But you have so much iron in the water that the Fe+2 precipitates into a mineral called vivianite, that's what happens. Okay, I'll go out and talk about some other things. So the model effect of iron and alum treatment. We tested phosphorus export with iron treatment in it, and it worked pretty well. 10 to 13% reduction in phosphorus export. We also tested phosphorus export with iron treatment, and it also worked pretty well. It worked a little bit better, between 11 and 24% reduction. Now, of course, this is a computer model. You aren't sure what's really going to happen, but it seemed to have worked. We also tested the effect of bubble aeration, and that would be using this type of bubbler here that you see, and it creates this look on the surface. I've seen them actually in Canada. They're very common in Canada on ponds. And, it didn't actually work as well. Minus 13.5% we used 2 models. One would be a simple aerator model, which is from it was from an equation developed out in California for deep reservoirs, and we applied it to these ponds. And then we used the Zeke-Stefan model, and the Zeke-Stefan model made a difference. The change in phosphorus export was 13.5% for Alameda and 8.8% for Camden Central, and that's with an airflow rate of 2.4 or 4.8 liters per second, which is a lot lower than what we had here. What we learned from these ponds is that they must be fully mixed. If they're not fully mixed, then you're going to export more phosphate, more phosphorus than you did before. So putting in an aerator and not fully mixing your pond doesn't seem to work that well, at least with this kind of aerator. And then we modeled the effect of watershed load reduction. We got a load reduction of 25% in volume if we put in infiltration basins. That's basically volume control. And also about 25% reduction in incoming concentration. That'd be street sweeping, and we had an 11 to 22% reduction in P export. That's a little bit lower than for infiltration basins, but it turns out that street sweeping is a lot less costly than building infiltration basins. So here's the results of all the computer simulations we did. This is the cost of dollars per kilogram of phosphorus exported. Not phosphorus coming into the pond, but phosphorus exported. So if you want to reduce the phosphorus that your pond is exporting, here are your choices that we worked on. We worked on also, so iron filings and alum treatment were about the same. Infiltration basins were more expensive because you have construction costs and things like that. You have to build the infiltration basins or the rain gardens or whatever. Intense street sweeping, that would be, street sweeping 24 times a year, maybe 30, 40 times a year. Probably 30 times a year would be enough. I don't know. Somebody has to tell me what's intense street sweeping. But that's how often you have to sweep your streets. I had a city engineer tell me they did intense street sweeping, and he said they're sweeping 4 times a year. And I said I wasn't sure that was intense street sweeping. Anyway, that is most cost effective. The best thing you can do is source reduction with street sweeping. That's still the best. Even better than treating the bottom of the pond with alum. Now, if you have internal phosphorus release, treating the bottom of your pond with, and I'll talk about this later, with alum and street sweeping, actually that's a pretty good combination. So this actually includes the cost of a regenerative street sweeper amortized over 10 years. So now let's go on to the field. We're talking about field comparisons. We're talking about doing things in the field. We did alum treatment. These are actual real life comparisons of before and after you do the treatment. So we did 4 alum treated ponds before and after they're treated. That was done by Joe Bischoff and Bar Engineering. We did 3 iron treated ponds. And we're also doing dredging ponds, and I'll show a little bit about dredging. And finally, we're doing currently aeration in 1 pond, and we're doing 4 more. But that work isn't completed yet. And these are the types of ponds treated. And you can see we've got a variety of looks, duckweed in some, no duckweed in others. So the alum treatment, that actually works pretty well. If you have a before, here's your sediment P flux in milligrams per meter square per day of 7.5. This is an example for LP53 in Egan, 7.9, about over 7 before, and virtually 0 afterwards. At JP5, it didn't quite work as well. You had 5.1 before and about 0.7 afterwards, but it's a significant reduction in all cases. In the sediments, the aluminum-based phosphorus went up because of the alum that you added. The labile, organic phosphorus, went down, and I'm not sure what's going on there. I think that is that the alum is grabbing all the phosphorus coming from the labile organic degradation. And the iron-based phosphorus actually went down. That makes sense. So we tried iron filings. We did the same thing before and after. And the iron filings before were very high. You can see the yellow is the anoxic SRP flux, soluble reactive phosphorus flux from the sediments. And the blue here is the oxic SRP flux. This is the pond that had a really high oxic flux. It's the highest I've ever seen. and we added the iron filings and everything disappeared. The other thing that's interesting is that S max on here, that's the gray bars. That is the maximum oxygen demand. The maximum oxygen demand also dropped, which tells me that we're doing something to the sediments. I don't know what we're doing, but we're doing something to the sediments when we add iron to them, or probably alum. We don't have S max we don't have the DO flux for the alum. But 3 years later, the anoxic flux starts to come back. Everything else stays the same. So iron filings work, but they don't work as well as alum. That's what we discovered. Their cost is about the same. And then there's dredging. Now, when I started this project, when I proposed this project actually, one of the reviewers said, The proposal was, let's determine what dredging would do to phosphorus release from the sediments. Is dredging going to decrease phosphorus release or not? Or maybe actually increase it? I didn't know. So we said, let's find out what happens, because they're dredging quite a few ponds. And so something's happening there. One of the reviewers said, well, everyone knows this. Everyone knows that dredging reduces phosphorus release. And I said, I don't know that. I looked in the literature and I didn't see it anywhere in the literature. So we investigated it. And the answer is maybe, maybe not, but not that much. So if you take a look on the bottom right, we have a anoxic sediment P flux versus on 5 different ponds. And we have 2 ponds here have basically the same. That would be 95 and NW 15H. There's no change. On one pond, it was reduced by 2/3, that'd be 128. On 175, it was reduced by 1/3. And on 28.19, it was reduced by half. It's just not that big of a difference. It's not the kind of thing that you want in terms of treatment for phosphate. You have to dredge, but I wouldn't really dredge in order to treat, to reduce phosphate release. And the other thing is that if you look at the pie charts, there's not much change in terms of where the phosphorus is, where's the phosphate. So the last item is artificial aeration and mixing of ponds. We're working on this right now. We are working on it from a number of different points of views. We're working with nanobubble air addition, bubble aerators, and pump mixers. The pump mixers at the bottom, that's a solar bee. The bubble aerators are to the right, and the 2 nanobubble generators are in the middle. Those pictures in the middle. The thing about aerating ponds is that it's fairly expensive to aerate a pond, considering that we got so many ponds, right? But you might have a high value pond, like Shoreview Commons, where everyone's walking around the pond. It's part of a park system. Its amenities are very important. And for that, you might want to put in an aerator. The other thing is that the nanobubble generators, they put in small bubbles that do not rise because they're so small. They add oxygen to the sediments, and they consolidate the sediments. The people who sell them say that we can reduce the depth of the sediments, increase the depth of the sediments by 8 inches to a foot. So we increase the depth by 8 inches to a foot by adding these nanobubble generators. That could make a difference if you talk about avoiding dredging for 5 years. That might encourage people to put one of those in. Anyway, we're investigating those in the field. So I'm going to conclude with these statements. Alum treatment and iron filings will reduce phosphorus release, but alum works better. Dredging can reduce sediment phosphorus release, but not sufficient to eliminate P release, and not in all cases. We may need additional treatment to the sediments. And finally, intensive street sweeping is the most cost-effective option. So a really good option would be intensively sweep your streets, and if you have a problem with phosphorus release from the pond, put alum in the bottom of the pond, place alum in the pond. It'll work for at least 5 years, possibly longer. We don't know yet. So thank you very much. I'll soon turn it over to Joe Bischoff.
Thank you, Dr. Gulliver. And Joe Bischoff will be joining us for our next presentation on pond treatments. And there is a Q&A in the Pigeonhole app for questions for John and Joe. If we wrap up by 1:45, we will do those Q&A right now. Otherwise, we will save those for the panel discussion this afternoon. Thank you, Joe.
Thanks. Great, so now that we know that alum is the best thing to do, that we all want to put alum in our ponds, right? So I'm going to talk about using alum for phosphorus inactivation in stormwater ponds, just kind of going through our experience, what it takes to implement a project, how you make an effective project, and going through that whole process. It's not for the faint of heart, but it is very doable when it comes to implementing the projects. I just want to thank some of my partners, Eden Prairie, Egan, Riley Purgatory, Bluff Creek Watershed District, and University of Wisconsin Stout. They've been a big part of this project. I'm going to show you a lot of work from Egan. Egan's been collecting a lot of data, and we should be very appreciative because that data has helped us learn a lot about how to implement these projects, where they work, where they don't, and how to make good decisions when we go through that. So the first question I want to talk about is, how do we decide what ponds we want to treat? It's difficult, right? We have hundreds of ponds, sometimes approaching 1,000 ponds in our city. How do we decide which one alum treatment or stopping sediment phosphorus release would really be helpful? Will it make a difference, and is it going to last? This is the McCarthy Lake watershed. You can see McCarthy Lake in the northeast part of the watershed there, and all these drainage. So we have all this pond and network. And so what we did is we identified the key ponds closest to the lake that were providing a lot of treatment. And we started there, and we asked the question, are they releasing phosphorus? Are they capturing phosphorus? And how do we work through that process? And then when we get to it, we have to think about the access and application technologies. If we decide to do these ponds, to treat them, how are we going to go through that process? Knowing that I prefer a liquid application, it works better, it binds better, but there are other ways to do this. We can use dry products and other things there. Okay, so I'm also going to talk briefly about the Mooney Lake watershed. I'll show you some ponds from this one. Mooney Lake's in the eastern part of the watershed there, and it has kind of a chain of ponds that travel from west to east, draining down into the lake there. So when we get to it, I'm a desktop limnologist, I joke all the time, right? Like, so much is done through Google Earth and stuff these days. So I start looking at these ponds on the aerial photos, and I start looking at bathymetry data that the city's collected. And we start to look at ponds that look like this. We say, great, we're going to core these ponds. We're going to get some sediment data, and I'll talk about what that looks like. We'll try to figure out what internal loading would be in those. But what often happens is we get to the field, or my field crew gets to the field, and I get a call. Because this is what the pond looks like. And they go, how are we supposed to core this? How are we supposed to collect data? There's not any water in most of the pond. The outlet is kind of covered up, and it's not really discharging. So I just want to say, it's not for the faint of heart when you start thinking about how do we collect data for some of these ponds. It takes a lot of field knowledge, visiting out in the field, and creativity. We were able, I'm going to show you data, to get cores from that pond and actually do release rate experiments, and it was very interesting. So what do? We go out to these ponds, we collect sediment cores from there, and then we want to measure how much phosphorus is coming out of those cores, right? Because we want to know if a pond goes anoxic or certain conditions, how much is going to release in the water column, and is it undoing what we designed that pond to do? We designed that pond to capture sediment, comes into the pond, settles into the sediment. We want to keep it there. That's the whole purpose of the pond, at least from a management of watershed phosphorus perspective. How do we keep it there, and if it's releasing, what's going to change? Okay, so I look at it as a pretty simple approach. It's really just, I'm looking for net pond sediment retention, and I'm looking at it's just the difference between gross settling, how much is actually reporting on an annual basis to the sediments, comes into the pond from the watershed, it settles out, and then how much is being released. So we have to subtract out what that sediment phosphorus release is. So when we do a project, or a lot of the projects I see for municipalities, is we use P8. We say, look, we have all these ponds. They're doing a great job at holding phosphorus. We're settling this many pounds. We're going to set our TMDL off of that. But the part that we're missing is the sediment phosphorus release. Some of it's coming back out of the sediment. So you're using a gross sedimentation term to estimate net retention. So we're just going to look at it from this gross and net settling perspective by doing some release rate studies to understand how well those ponds are actually capturing and holding phosphorus. We do this by taking samples back to the lab. This is a lab setup at the University of Wisconsin-Stout. Barr's laboratory also has a similar setup. But what you do is you bubble nitrogen over the surface or in the top of the core. That makes it go anoxic. And then those anoxic conditions are simulating that field anoxia. And then we just measure over time the phosphorus release. Okay, so we can actually measure how much phosphorus is coming out of those cores in those conditions that are in there. So we do that, and then we can compare that to our sedimentation term. We're using P8 or PondNet in our case. PondNet is built for the city of Eagan. So we have in there sedimentation terms. We have an estimate how much phosphorus are we actually capturing in the sediments, and now we have an estimate of how much is releasing back out of the sediments. So we can ask the question, how efficient is this pond really working in terms of phosphorus capture? Okay. So what does that look like? Here's some sediment phosphorus release rates from the city of Eagan. What I can tell you is they're all over the place, right? I think one thing you might, at the end of this talk, you're gonna learn is all these ponds are so variable, it's very hard to predict some of these conditions. I've struggled with trying to be predictive of it. So each pond has to have kind of its own set of information. I wish it was easier. I wish I could just tell you, go put 150 grams aluminum per meter squared in your pond, you'll be good. It's too variable right now for us to get to that point. So these are those ponds, that chain of ponds is on the top there of 37, which drains into 36, which drains into 35. Those phosphorus release rates were between 8 and 12 milligrams per meter squared per day. That can be a significant amount of phosphorus. That rate looks high compared to lakes. But we have to do that mass calculation to figure out how many pounds are actually being released, right? Because a small pond only has a small surface area. That may be a half a pound per year. I'm going to show you that in a minute. Okay, so we take these release rate data and use that to estimate how much is coming out of the sediments. But we know that sediment release is driven by anoxia, right? So now we have to somehow figure out how to estimate anoxia. And this is where I bang my head against the desk more often than not. So we've been using the St. Anthony Falls Pond tool. They have some great regression equations that are looking at things like duckweed coverage. How can we predict that anoxia or that anoxic factor, which is just these ponds on the left, that orange that's the maximum anoxic area we measured in those ponds. I'd say we, but it was Saffold that did a lot of the field work. And then we can use these equations that are done on the right to try to figure out how much anoxia there is, okay? So to me, the most challenging part when we're thinking about managing a stormwater system for phosphorus retention is understanding oxygen dynamics in the ponds. That's the piece that we really struggle with because it's data intensive, it takes a lot of work to collect it. How can we predict that? These are some great starts to trying to figure out how to do that. So I take the release rate data, I take my sedimentation data, and I say, okay, let's just do a mass balance of that. And I get a table that looks something like this. I don't want to go through all the details of the table, but there's things that I want to look at is like, what's the size of the pond? And then if we look at our phosphorus flux numbers in the bottom, I can calculate what's the total phosphorus load coming to the pond, what's the internal phosphorus release, what's the sedimentation rate, those come out of my modeling tools. And then my PondNet P retention, and then my actual net retention. So if you look at PondNet for JP 8.1 and JP 8, it would say that my retention is 57 to 43% phosphorus. We're feeling really good about that, right? Like that if I could have a pond functioning at that level, I would feel great. But when we add in how much is actually released out of those sediments, then we reduce it to 23% and 11% retention. So that sediment phosphorus release is a really important process when we think about designing or using ponds for phosphorus retention on a watershed scale. So we can look at this visually too, which is just taking those net flux numbers. So these are some different ponds. I didn't have a chance to do it for the Eagan ponds, but the blue bar is the sedimentation term. The orange bar is the sediment phosphorus release rate, and then your gray bar is going to be your net retention. So all of these ponds are doing positive things for phosphorus. I'm not bashing ponds by any means, but they could be doing better, especially when you look at what's that pond 1911B, and then the other one at the end, when you have that 7.5 or 7.7 pounds of phosphorus released. That's reducing our effectiveness. Now, also notice that some of these ponds are really small, so we're talking about 1 pound of phosphorus per year. So you have to put that in perspective of your receiving water to understand, does 1 pound make a difference? Maybe small ponds aren't really good candidates for alum treatments. We want to get the larger ponds that have large areas releasing phosphorus and those larger fluxes of phosphorus coming out of those sediments. I would also encourage you to think about this on a watershed scale. This is that same kind of flux, but for 3 different watersheds that we worked on. This is the Mitchell Lake watershed, the Riley Marsh watershed, and the Lake Riley watershed. And what you'll notice is that the ponding is really pretty effective in both Mitchell and Riley and Rice Marsh watersheds. We have a lot more sedimentation than we have for potential release, but look at this Lake Riley watershed. We actually, because we have so much wetted sediment in the watershed, we actually have more potential for release out of the sediments than we do for capture through sedimentation. So this is a real problem. Can you overpond your watershed? Absolutely. Because what you're doing is you're creating these wetted sediment areas that can flux phosphorus back out much more efficiently than you can from even upland soils in some of those areas. So you always think, oh, I'm going to oversize my pond. That sounds great. Maybe not. Okay. And this is the Lake Riley watershed. This is Bear Path, and see all the big ponds they have in there. It ended up with this really heavy percentage of wetted width and flux that comes out of there. Okay. So if we've gone through this process, we've collected sediment data, we understand the flux and the net retention in these different ponds. How do we start to figure out how much alum to put in if we want to inactivate the sediments? Okay, we want to take those orange bars and we want to knock them down to 0 so we're not releasing out of those ponds. How do we go about doing that? Well, the dosing process is stoichiometric, meaning that I'm just going to apply an aluminum ratio to how much phosphorus I want to bind. We did this based off of a number of studies on lakes where we predicted where we got 90% binding efficiency. So we did an assay, we took fresh sediment, we added alum until we got 90% binding, and then we asked the question, how much aluminum did we have to put in for the amount of phosphorus that was in there? Okay, so we did a bunch of these assays and we figured out, oh, this is actually predictable among different lakes. And it says that it's kind of counterintuitive, but basically as you increase the amount of mobile phosphorus that's in the sediments, you actually have to put less aluminum in to bind it and keep it in the sediments. It's just much more efficient. When that concentration's higher, it's much more efficient at finding that phosphorus and binding on it. When it gets lower, you have to overwhelm the sediments to some point to be able to get that aluminum to find that phosphorus that's in there. Okay, so we use this predictive relationship, but I would please don't use it as a plug and chug equation if you go out and do this for your pond, because when you get into the steep part of the curve there, small changes in redox P mean major changes in the amount of aluminum you have to put in. So there's a little bit of artwork when you get into those lower concentrations when we do this. So I've been talking about mobile phosphorus, right? And well, what is that? What does that even look like? How do we measure that? Well, we do what we call sequential phosphorus extractions from the sediment. So we'll take those back to the lab, we expose them to different extractants, whether it's an acid or a base. We measure how much phosphorus comes out in each one of those steps, and then we assign it to a source. So we might say we'll expose the sediments to a 1 molar ammonium chloride solution. You can use deionized water. We'll measure how much phosphorus comes out in that extractant, and then we assign that to what we call a loosely bound fraction. That means that's phosphorus that's kind of in the pore water or bound really weakly to something in that area. So it easily would flux out of the sediments. And then we take the next step. We look for iron bound, and we use a 0.11 molar sodium bicarbonate, dithionite, and on and on. I won't go through all of those. But we do the sequential extraction, then we assign it to iron-bound, labile, organic. If you look at those first 3, loosely bound, iron-bound, and labile, we consider those mobile phosphorus fractions, meaning that those are susceptible under the right conditions to recycling up into the water column and fluxing out of the sediments. Okay? And then you have something like aluminum bound, we call that semi-permanent. It's effectively permanent in the environment, but if you got your pH above 9.5 or your pH below 6, you could mobilize that, that aluminum and the phosphorus bound to it. Okay, so we do these lab measurements. We've done this for lots and lots of ponds in the Riley Purgatory Bluff Creek Watershed District and in Egan, and it's incredibly variable. I wish I could tell you that it was very consistent, that we saw similar amounts, but it's not. So the orange part here is the iron-bound fraction. That's the fraction that's most susceptible to release under anoxic conditions. Okay, and you can see in some ponds, it's a huge pool in there. Sometimes it's a much smaller pool. The gray bar, I think, is the labile organic fraction. Sometimes these ponds are more organic bound phosphorus and less iron bound. So what I want to tell you is to dose, to figure out how much aluminum to put into the pond, we need these data to predict that. If it was consistent across these ponds or it was predictable, then we could come up with this kind of thumb like, yeah, maybe put in this amount. But because it's so variable, we're having a really hard time figuring out how to predict what those numbers are. And then what's driving that internal phosphorus release is also quite variable. Right? Sometimes, most of the time, it's iron-bound phosphorus, but there are some ponds that have very large labile organic phosphorus concentrations, and those could be driving that part. Okay, so we've done our coring study. We figured out how much aluminum to put in. Well, what the heck is alum? We've been talking about it for 2 days now, and nobody's really defined what alum is, so I thought I would just go through that real quick. It's really just aluminum sulfate, which comes from, it's a liquid. You basically boil aluminum, raw aluminum, in sulfuric acid. You form aluminum sulfate, and then we add that to the lake. When you add it to the lake, it hydrolyzes and precipitates out into that white precipitate you see in these 2 pictures here. That settles into the sediment. That's now aluminum hydroxide that binds with phosphorus, and that binding is permanent. Okay, so what we're doing is we're basically just taking that phosphorus and keeping it in the sediments. Even if that resuspends, I know we've talked a lot about resuspension, it can't grow algae. Algae can't access it once it's in that aluminum hydroxide bond. So even if it resuspends, it's not going to dissociate and grow algae, so it's this permanent inactivation. So that's why we call it sediment phosphorus inactivation. I am now rendering that phosphorus useless to algae so that we can't grow more algae that's in there. Okay, so we go out and we do that. We've done this for lots of ponds. We've done lots of doses. We haven't applied it in all those ponds, but in the case of these, it's pretty variable in terms of those doses. Now, the dose isn't, if you look at a handful of these ponds, they're really in that 100 to 150 grams aluminum per meter squared. There is a pretty consistent route there, but you get a few of these, like the 2 in the box here, that are quite different. Well, why are these 2 different? They have very different concentrations of iron-bound phosphorus. That's the red line going in the depth. Those are 2 centimeter sections. So we look at a profile that's in there. But on the top, that's your moisture content. So look at the density differences between these 2 ponds. On the right in JP8 South, we have really loose, unconsolidated sediments in the top 10 centimeters. And so that's going to be a much lower mass of phosphorus we have to reduce. And if you look on the left in JP 8.1, those are very dense sediments to where it is. In those cases, we worry about alum sitting on the top because it won't integrate into the sediments if it's too dense. And then it's available for resuspension or flushing out of your system and some of those other projects that are out there. So dosing is important. It's important to look at the density of your sediments. It's important to look at those mobile phosphorus fractions and try to develop an understanding of how that aluminum is going to interact with your sediment for binding that through the system. So now the question everybody wants to know is, how much does this cost? Is it expensive? It's not. For ponds, it can actually be really inexpensive because you're treating such small areas. So these are just alum costs on the left. This is I converted everything to $2026. So we've done some recent bidding. I just took those recent bid numbers and took the dose and recalculated what those costs would be. And really, most of the ponds are between $5,000 to $10,000, $15,000 in terms of those applications. Now, if you go to an applicator and you say, I want to do this pond, and it's a $2,000 bid, they're going to laugh at you, right? It's really hard. It's an effort to get out in the field and do this application. I'll show you that in a minute. So you have to package these together. We've been really successful in Egan of packaging them with some other lake projects that we might have, or packaging enough ponds together so that it's an attractive bid for the contractor to go out and do that. And then when you look at the just cost per acre, that's on the right side, it's really can range, pretty typically between $5,000 and $8,000 per acre. You can get some of these higher doses that are closer to $20,000 per acre. So really, it's a pretty affordable way to bind phosphorus and increase the efficiency. The challenge is finding a contractor and getting it put into a pond. Okay, so let's talk a little bit about the implementation of that. So one of the things about alum is you have to control pH when you do the application process. If the pH drops below 6, the alum changes species, and that becomes toxic to fish and macroinvertebrates. It binds to the gills, and it basically chokes them out at that point, okay? So we gotta manage that. We wanna make sure that we keep